Okay, welcome everyone to our ZAC seminar. My big pleasure to introduce Alex Perry from University of Michigan, Ann Arbor. And Alex will speak about his joint work with Sasha Kuznetsov about Spherical Functors of semi-orthogonal components.
All right, well, yeah, thanks a lot for having me speak here. So yeah, I want to tell you about this work with Sasha Kuznetsov. And I think I'll start just with a little bit of motivation for the main result that I'll be telling you. Maybe I'll just start by saying that I'll work for simplicity over the complex numbers, although some things can be said more generally. Oh, and before I forget, let me share a link with the notes for the talk in the chat. So if you follow that link, you can see my notes, which you have to refresh in real time if you want to see the current version. Then you can go back and see what I wrote earlier. Okay, so yeah, so let me start with sort of the main motivating example for the talk. And so that's the following. So let's consider X inside of Pn, a Fano-complete intersection. Of type, so let me say of type D1, D2, up through dk. So X is a complete intersection of hypersurfaces of those degrees in projective space. And when you have such an X, then there's a nice decomposition of its derived category. So more precisely, you can look at the following line bundles on X. So they're just twists of the structure sheaf. And here, the index is the positive number, n plus 1 minus the sum of the degrees. And this sequence of line bundles is what's called an exceptional sequence. In the derived category of X. So this is in d of X. And in this talk, d of X will always denote the derived category, So it'll always denote the derived category of perfect complexes on a variety X. And so, it's pretty harmless. For most of the talk, you could just assume X is smooth, and then this is just dBco. So the bounded derived category of coherent sheaves. And so let me just recall for you, what does it mean for this sequence to be an exceptional sequence? It means two things. So first of all, it means that if you look at the self X from any of these objects to itself, then it's just a copy of the ground field concentrated in degree 0. And another way to say that condition, so this implies, and in fact it's equivalent to, the statement that the triangulated subcategory generated by this line bundle inside of d of X is a copy of the derived category of a point. Okay, so we have a bunch of these objects who have this X condition on the self X, and moreover, there are no X in one direction between the objects. So X from O of I into O of J is 0 whenever I is bigger than J. Okay, so that's the definition of an exceptional sequence, and it's not too hard to see that for one of these Fano-complete intersections, these conditions hold. And the upshot of having this exceptional sequence is that you get a semi-orthogonal decomposition that looks as follows. So a bunch of the pieces in the decomposition are just those line bundles I wrote. And then there's an interesting piece, which I'll call Rx. So this is a semi-orthogonal decomposition. And here, this category Rx is by definition everything which is right orthogonal to the objects O through O index minus 1. So by definition, it's the full subcategory consisting of objects E, which receive no X from these objects. So this is for I between 0 and the index -1. Okay, so this thing that I wrote down is an example of a semi-orthogonal decomposition. It's a way to break your category dx into a bunch of pieces which is semi-orthogonal in the sense that there are no Hams going from the right to the left. And it's a decomposition in the sense that these categories generate d of x as a triangulated category. And so this is sort of one of the main motivating examples for the talk. And this category here, R of x, is what's called the residual category of x. Or it's also pretty commonly called nowadays the Kuznetsov component of x. And since this is a joint work with Sasha, I decided to follow his wishes to call it the residual category. So I'll try to refer to it as that today. But the way you should think about it is that this is the category, this category Rx is like the interesting piece of the derived category. It's what you get when you remove a bunch of copies of the derived category of a point, which naturally sit inside of d of x. Before we get into maybe the main result that I want to tell you about, let me just try to, motivate the study of these residual categories. So recently, people have been thinking about them for several different reasons, and I'll mention two of them here. Oops, and also let me just add some pages to my. I forgot to add pages. 1 second. Okay, maybe that's enough. Let's see. Okay, so here's just a little summary of some of the reasons why people are interested in these categories. So interest in residual categories. And I'll mention sort of two different reasons you might be interested. So the first one is because of relations, often conjectural, to birational geometry. Okay, and let me just mention maybe the most famous conjecture in this direction. So here's the conjecture due to Kuznetsov. So what it says is that, let's say that we look at a very special Fano complete intersection. So just a cubic hypersurface of dimension 4. So that's usually called a cubic fourfold. So it's again a smooth degree 3 hypersurface in P5. Then Kuznetsov's conjecture is that X is rational if and only if this residual category is equivalent to the derived category of a K3 surface. Okay, and there's a lot of history behind this conjecture, and it's sort of motivated a bunch of work in this area recently. But maybe the only thing I'll say is that this conjecture is like a very strong conjecture. For instance, it turns out to imply that a very general cubic fourfold is not rational, which is sort of one of the really big open questions in classical algebraic geometry. So yeah, this is maybe the only thing I wanted to say to highlight the fact that in general, there are a lot of conjectural relations between these kind of residual categories or more general semi-orthogonal decompositions and birational geometry. Any questions before I tell you one more piece of motivation? Okay, cool. So the other, one other direction that I wanted to mention is that moduli spaces of Bridgeland stable. Of Bridgeland stable objects in these residual categories. So my notation for such a moduli space will be M sigma Rx V. So here sigma is supposed to be the stability condition, and V is just you can think of it as like numerical data for the objects you're parameterizing. So technically, it's an element of the Grothendieck group of your category. it's not so important for what I'm going to say. So you can look at moduli spaces of Bridgeland stable objects in these categories. And let me say they have a rich structure. So I'll mention two results which kind of highlight that. So the first one is a theorem that I proved in joint work with several people. So this is Bayer, Lahose, McCree, Newer, and Stellari. And what we showed is that, again, let's consider a cubic fourfold. What we showed is that these spaces, M sigma, are hyperkähler. Projective hyperkähler varieties of expected dimension. Okay, so there's some formula for the expected dimension, and what we showed is that when that number is positive, that the space is non-empty and it has that dimension. And maybe I can just, so this is, I'm just really briefly summarizing the theorem that we proved. But in particular, one thing that you get out of this is if you vary X, if you vary the underlying cubic fourfold, this gives an infinite series of unirational, locally complete families of polarized hyperkähler varieties. Okay, so what I mean is you fix this numerical data V, and then you vary the cubic fourfold. And over the moduli space of cubic fourfolds, you get a family of hyperkähler moduli spaces. And these are actually locally complete families of polarized hyperkähler varieties. And the moduli space of cubic fourfolds is unirational. That's why I wrote unirational here. So people have been trying to construct these kind of families of hyperkähler varieties for a while. And before this result, there were only like finitely many cases, but this sort of gives the first infinite series. So this is maybe one indication that moduli spaces of objects in these categories can be interesting. And let me just mention briefly one other result. So for a different class of hypersurfaces. So you can consider these moduli spaces of Bridgeland stable objects more generally. And for instance, you could consider them for Fano threefolds. There's been a lot of work. So I just want to mention one result in this direction by Pertuzzi and Yang. And what they showed is that if X is, say, a cubic threefold, so one of the one of the most like fundamental Fano threefolds, then these moduli spaces are actually always smooth. Okay, which I think is pretty interesting. So it sort of gives this infinite series of canonically associated smooth varieties to any cubic threefold. And these kind of moduli spaces have been useful to prove Torelli kinds of theorems for Fano threefolds. Okay, so that's what I wanted to say about motivation for why you might study these categories. Any questions before I get into the main result for today? Okay, cool. So yeah, so it turns out in both of these classes of results, a really important ingredient is an understanding of the Serum functor of these residual categories. And so let me just start by defining what a Serum functor is in general. Oops. So definition. So a Serum functor is kind of like a version of the canonical bundle, or maybe the dualizing complex of a variety for a category. And more precisely, a Serum functor for a triangulated category, let me say C is an autoequivalence I'll call it S sub C such that we have isomorphisms as follows. So Hams from E to F should be isomorphic to Hams from F into the Serum functor applied to E, dual. And these isomorphisms should be functorial in the objects E and F in our category C. Okay, and just to connect, if you haven't seen this before, to connect it with something you are familiar with, let me say, for example, if X is a smooth proper variety, then its derived category has a Serum functor, which is just given by tensoring with the canonical bundle and shifting by the dimension of the variety. So for instance, for E a vector bundle, the fact that this S dx is a Serum functor recovers classical Serre duality. So it recovers the fact that HI of E is isomorphic to the following thing. Is isomorphic to the usual thing from Serre duality. So the Serre functor is like a generalization of Serre duality to an arbitrary category. And like I was mentioning before, an understanding of the Serre functor for residual categories was kind of a key input in these theorems above, or in this conjecture. So let me just mention the theorem of Kuznetsov that tells you the structure of those Serre functors. So what it says is, okay, and so the important thing is that this theorem is only true for Fano hypersurfaces, this theorem that Kuznetsov proved before. So let's say that we have a Fano hypersurface of degree D. Then the theorem says that a certain power of the Serre functor, so the degree divided by a number I'll define in just a second, is isomorphic to a shift. So it's isomorphic to n+1 times D minus 2 divided by C, where here C is equal to the GCD of D in n+1. Okay, so the exact form of this expression here isn't super important, but the main point is that some power of the Serre functor is given by a shift. So for example, in this case of a cubic fourfold, if you just work out the numbers, what this says is that the Serre functor is equal to a shift by 2. So like in this case, right, that's saying that the Serre functor looks a lot like the Serre functor of a K3 surface. And that fact is sort of one of the motivations for the conjecture here. And it's also important for this theorem here because the fact that the derived category behaves like a K3 surface from the perspective of Serre duality turns out to give rise to the holomorphic symplectic form on these moduli spaces. So this result of the Serre functor about the Serre functor is really fundamental for understanding these categories. And my goal today is to tell you about a generalization of this theorem, which in particular applies to complete intersections, which is like a natural question: what happens for higher codimension complete intersections? Okay. I'll pause for a second, just take a sip of water. Okay, maybe I can keep going. Maybe one other comment I can make about the theorem is that I think it's a little bit surprising, because one way to think about this is it's saying that the derived category of these Fano varieties, well, first of all, they're sort of controlled by the residual category. That's the interesting piece of the derived category. But these residual categories are actually kind of like Calabi-Yau. They're either Calabi-Yau or what's called fractional Calabi-Yau, in that their Serre functor is at least up to taking a power, it's given by a shift. So in that sense, these categories are kind of opposite from being Fano. So I think that's kind of a surprising fact about the derived categories of these Fano hypersurfaces. So yeah, so I want to tell you about this generalization to the higher codimension. And to state the generalization, I need a little bit of terminology about something called spherical functors. So let me remind you about that now. So here's the definition. Let's say that psi from C to D is a functor between triangulated categories. And I'll assume that there's a right adjoint to this functor. Okay, and in this setting, you can always define something which I'll call twist functors, which are certain endofunctors of C and D. So I'll denote them as follows. So this one is an endofunctor of C. And then there's this other one, which is an endofunctor of D. And they're defined as follows. So they're defined by exact triangles. So what you do is you look at, for instance, you look at the unit of the adjunction, which is a map from here to here, and you take the fiber of this map. And that defines this, this first endofunctor. And similarly, you can look at the co-unit of the adjunction. And you can take the cone of this map, and that defines the other twist functor. Okay, and maybe I should say that technically here, to form these cones of functors, you should work in a suitably enhanced setting. But for instance, we're going to be interested in this in the case of residual categories, where there's a canonical enhancement of the triangulated category. So you don't have to really worry about problems with taking cones in the setting that we'll be thinking about. So you always have these twist functors, and we say that psi is spherical if both of them are actually, so a priori they're just endofunctors, but if they're both autoequivalences, then we say that psi is spherical. Okay, so let me give you an example, like the first historical example of these things. So this is due to Seidel and Thomas. So let's say that X is an n-dimensional variety and E is an object in the derived category. Then you can look at the following functor from D of a point into D of X. And it's the functor which just takes the complex and it maps it to V tensored with E. So that's a natural functor associated to any object in the derived category. And the statement is that this is a spherical functor if and only if the following explicit condition on X groups holds. So Xi from E to E should be concentrated in degrees 0 and n. And in those degrees, it should be given by a copy of the base field. Okay, so that's the first part of the condition. And the second part, so both x0 and xn are one-dimensional. And the second condition says that those are both one-dimensional. They have the same dimension for a good reason. Namely, the Serre functor applied to E should be isomorphic to E shifted by n. Okay, and so the statement is that this functor here being spherical is equivalent to these two conditions holding. And this first condition says that the X groups look like the cohomology of a real n sphere. So that's where the terminology spherical comes from. So for instance, you know, an example of these kind of objects would be if E was like a line bundle on a K3 surface, that gives you a spherical object in the derived category. And in general, these these spherical objects and spherical functors have been pretty important in algebraic geometry because they're like a really rich source of autoequivalences. So I want to mention one other example of a spherical functor, which is more relevant for the stuff I'm telling you about today. So here's the example. Let's say that I is the inclusion of some divisor x in a variety m. Then you can look at the pullback functor on derived categories. Okay, in this talk, all of my functors will be derived functors. So this is the pullback functor on derived categories. And the statement is that this is spherical. And the reason is you can just compute that the twist functors are given as follows. So one of them is given by tensoring on M with this line bundle associated to X, and the other one is given by tensoring with this line bundle shifted by 2. Okay, so there's a computation you do to check that these twist functors are given by these formulas, but both of those are, manifestly autoequivalences of your categories. So that means that this functor is spherical. Okay, so this is the notion of a spherical functor, and using it, I can formulate the main result of the talk. So here's the main theorem. And again, this is joint work with Kuznetsov. So what we proved, so there's going to be several assumptions, and then there will be several conclusions. So the statement will be a little bit lengthy, but so let me tell you the setup for the theorem. So M will be a smooth proper variety of dimension, let's say n. I'll assume that the canonical bundle of M is of the form O of minus little m for some line bundle OM of 1. And here I'll assume M is bigger than or equal to 1. Okay, so the kind of thing that you should have in mind is M could be like a phono-complete intersection. And the derived category of M, I'll assume it has a decomposition that looks like the one I wrote down for a phono-complete intersection. So there will be some interesting piece, which is the residual category. And then there will be a bunch of other pieces, and they're twists by various powers of this line bundle. Okay, so here, BM is just some triangulated subcategory of DM, and this twist notation is sort of the obvious one. So you just take BM and you tensor it with this line bundle O of 1. That's what BM twisted by 1, for instance, means. So I'll assume that I have an M with a given semi-orthogonal decomposition like this. And finally, I'll let I be the inclusion of a divisor in the linear system OM of D, where D is some integer between 1 and M. And again, the way you can think about this is that M could be like a complete intersection of type D1 up through DK minus 1, and then X is like a further intersection with the degree D hypersurface. So that's the situation you should have in mind. And then the conclusion is the following. So first of all, the pullback functor on derived categories is fully faithful on this subcategory BM. So it's fully faithful on that category. The second statement is that the derived category of X has itself an induced semi-orthogonal decomposition that looks as follows. So here, Bx is by definition the image of this BM. And then the complement of those categories is what I'll call the residual category. And again, in the case, like I was saying, where X is a Fano degree D hypersurface section of a complete intersection M, this just recovers the decomposition I told you about in the beginning of the talk. And then the third part of the conclusion is that this pullback functor actually restricts to a spherical functor between the residual categories. So I'll call it psi from Rm to Rx. And the final part of the theorem, which is really like the main part, gives you a formula for the Serre functor of these residual categories in terms of psi. So it says the following. Let's assume that C, or let's call C the GCD of D and M. Then the statement is that the Serre functor of Rm raised to the power D over C is isomorphic to not a shift, but a power of this spherical twist composed with a shift. Okay, and the exact numbers that appear here aren't super important, but I'll just write it down to be precise. Okay, again, just to say it in words, what the fourth part of the theorem is saying is that a suitable power of the Serre functors is given by some power of the spherical twist associated to psi composed with a shift. So any questions about the statement of the theorem? I'll make some remarks about it, but first maybe I'll just see if the statement is clear.
Just a silly question. When you write OM of 1 and then you write OM of minus M, is that the minus mth power?
Yeah, exactly.
Thank you.
Yeah, no, sure, no problem. Any other questions? Okay, well, let me make a couple remarks about the statement of the theorem. So, remarks. So the first remark is that there are lots of examples of suitable M which you could take in this theorem. So examples of suitable M include complete intersections in Pn. More generally, you could look at weighted projective spaces, or you could also look at Grassmannians. So whenever you have a complete intersection in one of these spaces, it turns out there's a natural decomposition of this form. So there are lots of choices for M that you could take. And the one that you should really keep in mind is M could be like the Fano complete intersection in Pn. That would correspond to, the motivational example in the beginning of the talk. The second remark that I want to make is that the special case where this residual category Rm is equal to 0. So first of all, if Rm is equal to 0, then the functor psi is 0. And if you just look at the definition of the spherical twist, that will mean that the spherical twist is equal to the identity, both of these. So in this special case, which it implies that the spherical twists are the identity functors, this recovers Kuznetsov's, I'll call, say, fractional Clavial theorem. So namely, in this case, it recovers the theorem that I mentioned for you earlier, right here. So right? In this case, there's just a shift and there's no spherical twist appearing. And one way to think about that is it's because the residual category of Pn is equal to 0. In other words, Pn is just generated by the line bundles O up through O of n. But allowing this Rm to be non-zero is crucial for understanding higher codimension complete intersections. So that's the second remark. And maybe just the last remark I wanted to make is that there's a more general, I'll say categorical version of the theorem. So roughly where you replace d of m with some general category, you replace d of x with some general category, and you replace the restriction functor between them by a spherical functor. So there is some more general version of the theorem, and in particular, it applies to other geometric situations. So it applies, e.g., to double covers, x to m, where m is as in the theorem above. Okay. So that's the main theorem I wanted to tell you about, and some remarks about it. And so let me see. How are we doing on time? So I think actually what I'm going to do is, I'm not going to try to prove the theorem to you. It's a little bit technical, the actual proof of the theorem. I think instead I'm going to try to tell you about some applications of it. I'll pause one more time to see if there are any questions about the statement. Otherwise, I'll try to tell you some applications. Okay. Okay, so what can you do with this theorem now that we know a formula essentially for the Serum functors of residual categories of complete intersections? So here are the applications. Maybe I'll just start on a new page. So applications. So it turns out there's a way to use this formula to understand something called the dimension of these residual categories. So let me recall for you. So in general, I think it's actually a pretty subtle question to try to define the dimension of a triangulated category. And there are various proposals of what it should be. And I want to recall for you a nice recent proposal by Elegin and Luntz for what the dimension of a category should be. And so C will just, for this general definition, you can just take a triangulated category C, which admits a generator. Okay, so by a generator G, I mean that there exists an object so that the smallest triangulated category, which is idempotent complete and contains G, is equal to all of C. It turns out this is a really mild condition, like it's true for the derived category, for any semi-orthogonal component appearing inside of the derived category of like a quasi-projective variety, that semi-orthogonal component has a generator. So this is like a pretty mild assumption. So let's assume that we have a category with a generator. And I'll also assume that I'm given an autoequivalence, F of C. So in this setting, they actually define a notion of dimension, an upper dimension and a lower dimension of this autoequivalence. So the upper and lower F dimensions of C are the following numbers. So I'll write down the formal definition. It's kind of a mouthful, but then I'll tell you some properties about the definition, which should hopefully convince you that it's a reasonable one. So the upper dimension is defined as the following limb sup. Oops. So the limb sup over M of the following expression. So let me just write it. So what you look at is you look at X from your generator, into powers of your functor applied to that generator. And you look for the smallest I for which this is non-zero. You take minus it and you divide by m. And you take this limit as m goes to infinity. And similarly, for the lower f dimension, we'll look at the lim inf of an analogous expression. So this time instead, we'll look at the supremum. Okay, so here are two numbers you can define. They're measuring in some way what happens to this generator as you apply powers of the autoequivalence F. And we're going to be interested in a special case. So if C has a Serre functor SC, then you can define the notion of the Serre dimensions. And by definition, they're just given by taking F to be the Serre functor. So there's an upper Serre dimension, which again is just the upper dimension of the Serre functor, and there's a lower Serre dimension, which is the lower dimension of the Serre functor. Okay, and like I said, if you haven't seen these definitions before, they might, look a little bit weird, but so let me tell you these properties, which will hopefully convince you that it's a reasonable notion. So here are some properties that you can prove about this definition. Properties. So the first is that it's actually well-defined. So well-defined, i.e. independent of the choice of this generator G. So these numbers, this upper and lower dimension, they don't depend on the choice of generator. That's the first property. The second property is that the lower dimension is less than or equal to the upper dimension. Okay, that's reasonable. The third is that if X is a smooth proper variety, then these two Serre dimensions actually coincide. And they're both given by the usual dimension of X. Okay, so that is probably an important property that you would want to be true for this notion of dimension. And maybe one last property, which I'll mention that'll be useful for us, is that if your category is fractional Clapeyron, in the sense that some power by some integer, let's say p greater than 0, is isomorphic to a shift by an integer q, then the Serre dimensions are given as follows. So then the Serre dimension of C, the lower and the upper are equal to each other, and they're both equal to q divided by p. Okay, and actually these properties are not that hard to see from the definition I gave you. But they're nice properties, I think. I think this is a nice definition, and it seems to be an interesting question to compute this dimension in examples of categories that aren't D of a variety. And so the next theorem I want to tell you about gives you the answer in the case of residual categories of complete intersections. Any questions about this definition? Okay, cool. So let me tell you the theorem. So here's the theorem. So the theorem says, let's take X inside of Pn to be a smooth Fano complete intersection. And let's say of type D1 through dk. And also let me assume that all of these di are greater than 1. So maybe I should say with all di greater than 1. okay, if some of the di are 1, then it's not really interesting. You would just be in a lower dimensional projective space. So we may as well assume they're all bigger than 1. And then the statement is that there's just a very precise formula for the Serre dimensions of this category. So they're equal to the dimension of x minus 2 times the index of x divided by d max. That's the upper dimension. And the lower dimension is the dimension of x minus 2 times the index of x divided by d min. Okay, so d max and d min are just the maximum and minimum among these degrees di. And in particular, you see that the upper and lower Serre dimensions are not always equal for these residual categories. So one of our first motivations for proving this theorem, I'll just state this as a remark. So yeah, so one of the inspirations for this theorem was a conjecture of Katsarkav and Konsevic. So this was actually conjectured by Katsarkav and Konsevic in their study of the rationality problem for algebraic varieties. So they had some heuristics which suggested this conjecture. And actually, more precisely, they conjectured something a little bit stronger, a little bit too strong is what their original conjecture was. They conjectured that actually these numbers would coincide and both be given by this. And it turns out that that's not quite true. In general, these numbers are different, but they're given by these formulas that I wrote here. So this theorem proves like a modified version of their conjecture. So I'll tell you another application of this theorem in a minute, but first I wanted to just sketch sort of the idea of the proof of the theorem. So here's the idea of the proof. So we're going to use the formula for the Serre functors to prove the theorem. So let's say that this x, our Fano complete intersection, let's choose a presentation for it, M intersected Y, where M is a complete intersection of type D1 through dk minus 1, and Y is a degree D dk hypersurface. So you can always write your complete intersection X in this form. And the main theorem that I stated above tells you that in this case, the Serre functors look as follows. Okay, so I'm just going to write down the formula that you get if you plug in all of the numbers into that theorem. So what it gives you is that this power is equal to the spherical twist raised to the index of M divided by C, composed with the shift by this number. And for X, you get that this power is given by the twist to this power composed with this shift. Okay, and C as before is equal to the GCD of dk and the index of M. Okay, so this, I just unwinded for you, what the main theorem says in the case of these complete intersections. And the reason I did that is that it gives at least a hint for where these numbers here are coming from. So let's stare at this formula for the Serre functor of Rx. If this functor weren't here, if this were just the identity, then it would be saying that this category is fractional Calabi-Yau of dimension this number divided by d over c. So this divided by d over c, sorry, I forgot, this should be, sorry, there's a typo here. This d should be dk. Oops. Okay, sorry, that was just a typo. But if you divide this number by this number, what you get is exactly this expression here with d max replaced by dk. And similarly, this is exactly this number divided by this number with dk replaced with d min. And so the way you should think about it is that this category, it's not fractional Calabi-Yau, but it sort of looks fractional Calabi-Yau of different dimensions. And the largest one corresponds to the upper Serre dimension, and the lowest one corresponds to the lower Serre dimension. So that's not really a proof. That's just one way to see that these numbers come up somehow in the formula for the Serre functor. And the actual proof of the theorem is by induction. So maybe I can say, how does the actual proof go? So the base case of the induction is when X is just a Fano hypersurface. So when K is 1. And in that case, Rx is fractional Calabi-Yau. That was this theorem of Sasha's that I mentioned near the beginning. And in particular, in this case, the theorem does hold. That's just by this easy result that says that in the case of a fractional Calabi-Yau category, the Serre dimensions are equal, and they're both equal to this fraction that appears. So when the codimension is 1, it's not hard to compute the Serre dimension. And for higher codimension, you do an induction. And what you end up using are general inequalities, which you can prove relating the dimensions of the spherical twists on the source and the target. And this part of the proof relies on, to actually get these inequalities, it turns out there are some assumptions you need to prove. And what it ends up boiling down to is you need to prove some kind of non-triviality results for this functor psi. So this relies on non-triviality results for psi. So for instance, one thing that we prove along the way is that the kernel of this functor psi is equal to 0. So the restriction functor from the residual category of one complete intersection M to a further complete intersection X, that restriction functor between the residual categories actually has trivial kernel. So in a precise sense, the residual categories get more complicated as you go farther, like deeper into the codimension. But okay, that's all I really wanted to say about the proof. Basically, it's an induction using these general formulas here. Okay, and I have, I think, 5 more minutes. So maybe in the last few minutes, I'll just mention some corollaries of this theorem about the Serre dimensions that I stated. Any questions about this theorem before I keep going?
I have one question about the definition of F dimension.
Sure. Mm-hmm.
So you assume that it's has one generator G?
Mm-hmm.
Will that imply the direct category is just direct category of a point?
No, it doesn't imply that. So actually, the existence of a generator is a pretty weak condition. So for instance, like if you have like say X, which is a projective variety in Pn, if you take, say, O of 1 is the ample line bundle, if you take a direct sum of powers of O of 1 up to some fixed power, like roughly the dimension of X, it turns out that that direct sum of line bundles is a generator for the derived category.
Okay.
And more, it actually turns out to be, in general, pretty easy to have a generator. So it's actually a quite weak condition in general.
Okay, thank you.
Mm-hmm. Any other? Okay, cool. So maybe I can just tell you some consequences of this theorem about the dimensions. As I said, our first motivation for proving it was this conjecture by Katsarkav and Konsevic, but it has some other nice consequences, which I'll mention now. So the first corollary is that if this category Rx is equivalent to D of Z for a variety Z, then actually it follows that all of the degrees in the complete intersection are equal to each other. So I'll call this common value D. This common value D has to divide 2 times n plus 1. And finally, the dimension of Z has to be given by n plus k minus 2 times n plus 1 over D. So in other words, there is some very strong restrictions on when this residual category can be geometric. It can be given by the derived category of a variety. Like the most famous example is the one I mentioned near the beginning of a cubic fourfold. Sometimes the residual categories of cubic fourfolds are equivalent to the derived category of a K3 surface. And the possibility of this happening for residual categories of general complete intersections is actually pretty rare. So it's a very restricted condition. And what is the proof of this corollary? How do you see this? It's actually pretty easy. You just use the following observation. If there is an equivalence between these two categories, then it tells you that the Serre dimensions of these two categories are equal to each other. But the Serre dimension of D of Z is just the dimension of D of Z, and that's equal to its upper and lower Serre dimension. So you have these equalities. And now if you just go back and use these formulas that I wrote down in the theorem, it's not too hard to deduce the statement of the corollary. If you set both of these two things to be equal, the first thing that you conclude is that all of the degrees have to be equal to each other. And then if you just stare at it, you'll find that this divisibility condition holds and this dimension formula holds. So that's the first sort of easy corollary. And maybe one other corollary I can mention is that in the case where the degrees are not all equal, so let's say D max is bigger than D min, then there does not exist a Serre invariant stability condition on this category Rx. So precisely what do I mean by that? What is a Serre invariant stability condition? So one way to say that is that there is no fixed point for the following action. So we can look at the whole stability manifold. If you look at all of the stability conditions on a triangulated category, they form a manifold, which I'll call stab of Rx. And this manifold has a natural reparameterization action by the universal cover of 2x2 real matrices with positive determinant. If you don't know about stability conditions, it's not so important. But the point is that there's this natural quotient space which parameterizes all stability conditions on your category. And any autoequivalence acts on this quotient space. So in particular, the Serre functor acts on this quotient space. And the statement that I'm making in this corollary is that this action on this space of stability conditions has no fixed point. And that turns out to be a corollary of the theorem. And the proof idea is that actually what you can show is that, so you can show that the existence of an invariant stability condition implies that the Serre dimensions are equal. It's just some general fact which you can prove. And so once you prove that, this corollary immediately follows from the theorem about Serre dimensions. And maybe I can just mention like why is this corollary interesting? So it turns out that the existence of such Serre invariant stability conditions is important in the examples of Fano threefolds that have been investigated so far. So for instance, it's important for this result that I mentioned near the beginning about smoothness. Where is it? About smoothness of these moduli spaces for cubic threefolds. So in this case, there are Serre invariant stability conditions, and that's like crucial for this theorem here. So it was sort of a question about, there was a question about whether in general there could exist these Serre invariant stability conditions. And our corollary shows that actually it's quite rare in higher codimension. Okay, so I think that's all I have to say. Thanks for listening. Thanks.
Let's thank Alex on Zoom. Alex, thank you very much for excellent talk. Questions? Please ask questions.
Can I ask another question?
Yeah.
So I'm just curious about this fractional Calabi-Yau, the theorem you mentioned by Kuznetsov. It's for example, I'm thinking that if the Serre functor of the Kuznetsov component of a certain final hypersurface happen to be the same as the Serre functor of the Eric surface, is there any geometry related between them?
I didn't hear the end of your question. So if you have a hypersurface where the Serre functor happens to be, say that last part again.
Eric surface.
Oh, Enrique surface. Yeah, that is an interesting case. There are some examples where like the square of the Serre functor is shift by 4. There are examples of categories with that property. That's what it would mean to look like an Enrique. Like an Enrique surface has canonical bundle whose square is trivial. Right. So the Serre functor of an Enrique surface has square shift by 4. It's like fractional Calabi-Yau of dimension 2. And there are examples of residual categories with that property, which I think are interesting. I mean, it doesn't, I don't think just abstractly there's a lot you can say about a general category with this property, but there are interesting examples. Like there's something called a Gushel-Mukai threefold, which is a certain complete intersection in a Grassmannian 2-5. And that one has a Serre functor, which is like Enrique's type. So of the type that you're asking. And there is some interesting geometry associated with that.
So is there a relationship, geometric relationship between Eric surface?
So I don't know any, so in the examples I know, like for instance, in this Gushel-Mukai example I said, it's not true that the category is, it's true that the category is never equivalent to D of an Enrique surface. So I don't know examples of the following. I don't know examples where you have a category which is sometimes equivalent to D of an Enrique's, but generically not. So that's the situation that you have for like a cubic fourfold, but I don't know of non-commutative deformations of Enrique's surfaces in that way. And maybe those just don't exist, but yeah, I'd have to think for a second.
Okay, thank you.
Any other questions to Alex? Let me check chat. No, nothing in chat. Okay, if there are no more questions, let's thank Alex again. Thank you.
Thanks.
Okay, thank you very much. I will upload the video to the ZAG webpage in the evening after. When. Thank you. Okay.
Cool. Thanks.
Thank you. Bye.
Bye.
Bye.